Module 6, Lecture B, Feature Spaces. By the end of this lecture, you will be able to combine parallel transformations with FeatureUnion and make union, process heterogeneous columns using ColumnTransformer and column selectors, and inspect feature names, sparse thresholds, weights, and nested composite estimators. Parallel feature unions. Feature union basics. A feature union runs several transformations in parallel on the same input data, then combines their outputs into one feature space. This is useful when a model needs multiple views of the data, such as word level, character level, and document level features in text classification. Each transformer works independently, and the resulting features are joined side by side, so the model can learn from them together. Feature union is useful when different transformations capture complementary information from the same data. Instead of running transformations in sequence, where one output may limit the next, it runs each transformer independently and combines their results side by side. This lets multiple views of the data feed into a larger pipeline as one unified transformer before a classifier or regressor. When using a feature union, make each branch extract a different and useful view of the same input, rather than repeating similar information. For example, separate branches might capture color, texture, or shape in images, or different transaction patterns in fraud detection. Also consider how large the combined feature set becomes, and ensure the final model can handle it efficiently. Python code. Feature union basics. A feature union runs multiple feature transformations in parallel on the same input data. Each branch produces its own output, and the union combines those outputs into one feature matrix. This setup imports the main tools needed for a simple machine learning workflow. NumPy supports numerical operations, while Scikit-Learn provides the iris dataset and key utilities. Feature union combines multiple feature extraction steps. A function transformer applies custom data changes, and the standard scaler prepares features by centering and scaling them for better model performance. We load the classic iris dataset from Scikit-Learn for testing and demonstration. Its feature data is stored as a two-dimensional array, where each row is one flower sample and each column is one measured feature. We first validate the iris data to make sure it has the expected table-like structure. The data must be two-dimensional and contain exactly 4 columns, matching the 4 iris features. If either check fails, an error is raised to stop the pipeline before later processing problems occur. This branch scales the original features using Scikit-Learn's standard scaler. It removes the mean and adjusts values to unit variance, helping features on different scales contribute more evenly to the model. This transformation branch uses Scikit-Learn's function transformer to create squared versions of the input features. It applies a custom function that squares each value in the data, so every original feature is converted into its squared form. The output keeps a one-to-one match with the input features, meaning the number of features stays the same. A feature union runs multiple transformations on the same input data in parallel and combines their results into one feature matrix. In this example, one branch standardizes the features with a standard scaler, while another squares the features with a function transformer. This lets different feature extraction steps work side by side before their outputs are joined. A feature union applies multiple transformations to the iris data at the same time and combines their results. One branch standardizes the features, while another creates squared versions of them. The transformed outputs are joined into one feature matrix, giving a compact way to build a combined feature set from parallel processing. The code gets the feature names from the feature union, showing which branch produced each output column. Using the original iris feature names as a reference makes it easier to connect the transformed features back to the dataset, especially when several transformations run in parallel. The output checks that the Scikit-Learn version and iris dataset shape are as expected, then confirms that the feature union creates a wider combined feature set by joining results from both branches. It also shows a few output feature names to identify their source branch, and previews the first transformed row, rounded for readability. This script shows how Scikit-Learn's feature union combines multiple feature transformations in parallel. Using the iris dataset, it creates one branch that standardizes the numeric features, and another that squares them, then joins the results into one feature matrix. The combined output has 8 columns instead of the original 4, and the printed results confirm the new shape, feature sources, and sample values. This is a simple way to build richer feature sets within a single pipeline. Make Union Shorthand. The Make Union Shorthand makes it easier to combine parallel feature transformations without manually naming each branch. It takes transformers directly and assigns names from their types, which is useful for simple pipelines where the goal is to apply multiple transformations to the same data and merge the results. For example, in text classification, it can combine word and character pattern extraction while keeping the setup concise. The Make Union helper is useful because it makes experiments faster and easier to read. It lets analysts combine independent feature transformations in parallel, then merge their outputs before the next modeling step. This keeps prototypes clear and focused on the overall model structure, rather than on naming each component, which is especially helpful in notebooks and demonstrations. The Make Union helper is useful for quickly building simple feature unions, but its automatic names can become a limitation as pipelines grow. For complex, long-term, or collaborative projects, explicit branch names make tuning, auditing, and maintenance easier. In practice, use Make Union for quick, distinct transformations, and choose explicit naming when the pipeline needs clearer design and support. Python code, Make Union Shorthand. Use the Make Union tool to run feature transformations in parallel. Each transformation branch receives the same input data, and their results are combined into a single feature matrix. This setup imports the main tools needed for a simple Scikit-Learn pre-processing workflow. NumPy supports numerical operations, while the Scikit-Learn version can be checked for compatibility. The iris dataset loader provides example data, and pipeline utilities combine custom transformations with standard scaling, which centers features and scales them to unit variants. We load the iris dataset from Scikit-Learn, a small dataset often used for demonstrations. Then we keep only the first 2 feature columns, creating a smaller set of flower measurements for later processing and transformations. Before transforming the data, the code verifies that the input has 150 rows and 2 columns. If it does not, it raises an error to signal that the dataset has the wrong size or selected features. This check helps ensure the transformations are applied to the expected data structure. This branch scales the original dataset columns using Scikit-Learn's standard scaler. It standardizes each feature by removing its mean and adjusting it to unit variance, helping features on different scales contribute more evenly to the model. A transformation branch is created to produce squared versions of the input columns using Scikit-Learn's function transformer. It applies a simple squaring operation to every value in the data. The output keeps a 1-to-1 feature mapping, so each original column has a corresponding squared column. The make union function in Scikit-Learn creates a feature union that combines multiple transformation pipelines into one. Here, one branch scales the original features while another squares them, and the results are joined into a single feature matrix. This expands the feature space for later analysis or modeling, while automatically managing the branch names. The feature union fits and transforms the input data in one step by applying each branch to the same features. One branch standardizes the data, while the other creates squared features. The results are then joined side by side into a single feature matrix that combines both transformations. This step checks the feature union by retrieving and displaying its automatically assigned branch names, along with the Scikit-Learn version for reproducibility. It then compares the dataset's original shape with the shape after combining the transformed features, showing how the feature space expands when both branches are applied. We inspect the first row of the combined transformed features to see the result of the feature union. The values are rounded to 2 decimal places for readability, converted into a simple list, and printed. This gives beginners a clear example of how the original features were transformed and merged. This example shows how Scikit-Learn can apply multiple feature transformations in parallel using makeUnion. It loads the iris dataset, keeps the first 2 features, then creates one branch that standardizes them and another that squares them. The 2 results are combined into one feature matrix, expanding the data from 2 features to 4. The output confirms the branch names, the original and transformed shapes, and a rounded sample row to show the combined features. Transformer weights. Transformer weights control how much each transformation contributes in a feature union. Since multiple transformers process the same data and their outputs are combined, some feature groups can dominate because they have larger values or more columns. Applying weights helps emphasize important features or balance different groups, creating a more controlled and effective feature space. Transformer weights help combine different data representations when some are more reliable or predictive than others. They scale each transformer's output before the features are merged, without changing how the transformers learn. This lets the final feature matrix better reflect domain knowledge and stay balanced across inputs. Transformer weights control how much each feature block influences the model, so they should be chosen carefully. Larger weights can emphasize useful signals but may also amplify noise, while smaller weights can reduce dominance but may hide important information. In practice, these weights are best tuned through validation, especially when the model is sensitive to feature scale. This makes experimentation easier while keeping the model input balanced and interpretable. Python code, transformer weights. This example shows how weighted parallel feature transformations work. A feature union combines multiple transformed outputs from the same input data, and the printed norms illustrate how different weights change each feature's influence. This setup imports key tools for a simple machine learning workflow. NumPy supports numerical operations, while Scikit-Learn provides the iris dataset and utilities for building feature pipelines. FeatureUnion combines multiple feature extraction steps. Function Transformer applies custom data transformations, and Standard Scaler standardizes features so they are on a comparable scale. We load the small iris dataset from Scikit-Learn, a common choice for simple demonstrations. Its feature data is stored for later processing and transformations. The code first validates that the input data matrix is 2-dimensional and contains at least 4 numeric columns. If it does not meet this expected structure, it raises an error. This check helps prevent later processing steps from failing because of incorrectly formatted data. The code uses function transformers to split the dataset into two row views, one with the first two columns and one with the last two columns. In the iris dataset, these usually correspond to sepal and petal measurements. This separation makes it easier to process or analyze each part independently later in the pipeline. Two feature unions split the dataset into separate blocks for processing. One selects the first two columns using the first two transformers, while the other selects the last two columns using the last two transformers. This prepares each block consistently before weights are applied. We create an unweighted feature union that processes two parts of the data in parallel. One transformation selects the sepal measurements from the first two columns, while the other selects the petal measurements from the last two columns. This lets us combine both feature sets in one pipeline and compare their influence on the model without applying extra weights. A weighted feature union combines separate transformations for sepal and petal features, while assigning each one a different influence. The sepal features receive a weight of 0.5, and the petal features receive a weight of 2, so the final combined output emphasizes the petal features more strongly.
Before applying weights, we standardize the data so each feature is on a comparable scale. A standard scaler removes the mean and scales features to unit variance, then fits and transforms the dataset in one step. This makes the later effect of the weights easier to see. The scaled data is transformed in two ways. First, with an unweighted union, which combines the sepal and petal features equally, and then with a weighted union, which gives the petal features more influence. Comparing these results shows how feature weighting changes the transformed data structure. We compare sepal and petal feature sizes before and after weighting by measuring the average norm of each feature group in the transformed data. For both unweighted and weighted data, the sepal group uses the first two columns and the petal group uses the last two columns. Comparing these averages shows how the weights change the relative influence of the two feature sets after transformation. The output first checks the Scikit-Learn version to support reproducibility, then shows the shape of the transformed feature matrix. It compares the average norms of sepal and petal features before and after weighting, making clear how the weights change each feature group's scale. The key point is that these weights adjust feature influence before the groups are combined side by side. This script shows how transformer weights change feature transformations using the iris dataset. It splits the features into two groups, standardizes them, and compares an unweighted feature union with a weighted one. The weighted version reduces the influence of the first feature group and increases the influence of the second, which changes the average norms of the transformed data. This demonstrates how weights can control feature importance before the groups are combined. Column processing. ColumnTransformer basics. ColumnTransformer helps pre-process datasets where different columns need different treatment before modeling. For example, numerical features may need scaling or missing value handling, while categorical features may need encoding. It lets you assign the right transformation to each column and keep the full pre-processing workflow in one consistent estimator. ColumnTransformer lets you apply different pre-processing steps to different columns and then combine the results into one feature matrix. Each transformer learns only from its assigned columns, such as scaling numerical data or encoding categorical data. This keeps pre-processing organized, consistent, and helps avoid mistakes like applying the wrong transformation to a column. ColumnTransformer is commonly used as the pre-processing step in a machine learning pipeline, sending its transformed data directly to a classifier or regressor. This helps ensure that pre-processing is learned only from the training data and then applied consistently to validation and test data.
It can combine tasks such as scaling numeric features, encoding categories, handling missing values, and passing through engineered features. Its main value is making complex preprocessing reliable, consistent, and less error-prone as datasets grow. Python code, ColumnTransformer basics. This example shows basic preprocessing for specific columns. A column transformer applies different preprocessing steps to different columns, and the result includes the names of the transformed features. The script imports key tools for preparing data before machine learning. Pandas handles tabular data, while Scikit-Learn provides a column transformer for applying different preprocessing steps to different columns. It also imports tools to one-hot encode categorical features and standardize numerical features, along with Scikit-Learn itself to check the library version later. We create a small, varied dataset in memory using a pandas data frame, a standard structure for tabular data in Python. It includes numerical information such as age and income in thousands, along with categorical information such as region and membership tier. This mix of data types provides a simple foundation for demonstrating preprocessing techniques. We separate the dataset columns by type, so each can be preprocessed correctly. Age and income are treated as numeric columns, while region and tier are treated as categorical columns. This setup makes it easier to apply the right transformations to each kind of data. We first combine the numeric and categorical column names into one set of columns to process. Then, we check whether any of those columns are missing from the customer data. If a required column is absent, an error is raised, so the issue is caught early. This helps prevent preprocessing from failing later because of missing data. A column transformer lets us apply different preprocessing steps to different types of columns in a dataset. Numeric columns are standardized with a standard scaler, so they have a mean of 0 and a standard deviation of 1, which can help distance-based algorithms. Categorical columns are converted with a one-hot encoder into separate binary columns for each category, using a dense output for easier handling. Together, these steps prepare mixed data for analysis or modeling in an appropriate way. The preprocessor is fitted to the customer data and applies the right transformation to each column. Numeric columns are scaled, while categorical columns are one-hot encoded, and the results are combined into one transformed array. The code also retrieves the transformed feature names, showing how each output feature relates to the original columns and applied transformations. We create a new pandas data frame from the transformed data, so it can be viewed in a clear table. The column names come from the ColumnTransformer's feature names, which keeps the processed data easy to understand. This makes the transformed dataset ready for inspection, analysis, or visualization. This output checks the preprocessing workflow by showing the Scikit-Learn version, the original customer data shape, and the transformed data shape. It then displays the generated feature names to show how the inputs were encoded or scaled. Finally, it previews the first transformed row with rounded values, giving a quick sense of the changes made to the data. This script shows how to prepare mixed data for machine learning using Scikit-Learn's ColumnTransformer. Numeric features such as age and income are standardized, while categorical features, such as region and tier, are converted with one-hot encoding. The transformed columns are combined into one dataset, and the script reports key details such as the Scikit-Learn version, data shapes, feature names, and a sample transformed row. Column selectors. Column selectors help preprocessing pipelines apply the right transformations to each type of feature. For example, numerical columns may be scaled, while categorical columns may be encoded. This keeps composite estimators consistent and helps models train and predict more reliably. Column selectors choose which dataset columns to transform. Selecting by column name is usually clearest for labeled tables, while selecting by position works for unnamed arrays, but depends on a stable column order. Selecting by data type can automatically find numeric or text columns, but types do not always match modeling meaning, such as postal codes acting as categories or dates needing special handling. Effective column selectors depend on understanding both the data and the modeling workflow. Prefer robust selectors, such as those based on column names or data types, because they handle changes like reordered columns or added fields better than position-based choices. Good selectors help ensure each column is processed correctly, making pipelines easier to audit and deploy, while poor selectors can cause mistakes that hurt model performance. Python code column selectors. This example shows how a column transformer routes columns based on data type and applies the right preprocessing to each group. The resulting feature names make it clear what new feature space was created. We import pandas for working with tabular data and Scikit-Learn tools for machine learning preprocessing. A column transformer lets us apply different transformations to different columns, while a column selector helps choose columns by data type. We also use one-hot encoding to prepare categorical variables and standard scaling to normalize numerical features for many machine learning algorithms. We create a small pandas data table to represent customer information with mixed data types. It includes numeric fields such as age and income, along with categorical fields such as region and tier. This simple setup prepares the data for demonstrating how preprocessing can differ depending on each column's type. We use the make column selector function to automatically separate numeric and categorical columns in a data frame. Numeric columns are selected by choosing number data types, while categorical columns are selected by choosing object data types. These selectors help send each type of data to the right preprocessing steps later. A column transformer lets us preprocess different types of data frame columns in one pipeline. Numeric columns are standardized with a standard scaler, while categorical columns are converted to binary features with a one-hot encoder that returns a dense array. Each transformer is applied only to the columns selected for its data type. The preprocessor is first fitted to the customer data, so it can learn how to scale numeric features and encode categorical ones. It then transforms the data into a new feature matrix, and the resulting feature names are retrieved to show the structure of the processed data. First, verify that the transformed data has the same number of columns as there are feature names. This ensures every column is correctly labeled. If the counts do not match, raise an error so the issue can be caught early and the transformation remains reliable. This pre-processing check prints the Scikit-Learn version and the original customer data columns to support reproducibility and context. It then identifies which columns are numeric for scaling and which are categorical for one-hot encoding. Finally, it reports the transformed data shape and the generated feature names, showing how the original data becomes the final feature matrix. This script shows how to pre-process a dataset with both numeric and categorical columns using Scikit-Learn's ColumnTransformer. It automatically scales numeric features and one-hot encodes categorical features, then transforms the data into a new feature matrix. The script also checks that the transformed feature count matches the generated feature names and reports the final data shape and expanded feature names. Remainder handling. In column-based preprocessing, remainder handling controls what happens to columns that are not given a specific transformation. A column transformer can either remove these unmentioned columns or pass them through unchanged and combine them with the transformed data. This is useful when only some features need processing, while others should stay as they are or be excluded to avoid problems. In data preprocessing, leftover columns should be handled deliberately. Dropping them gives tighter control over what reaches the model and can help avoid unwanted bias in sensitive tasks. Passing them through unchanged is useful only when they are already in a model-ready format, such as numeric sensor data. Be careful, because unsupported formats, like text or dates, can cause errors if the model expects numbers. Handling remainder columns in a preprocessing pipeline helps keep the final feature space reproducible and understandable. When the pipeline is fit, the ColumnTransformer records which fields are transformed and which are passed through. So future data should keep the same structure to avoid unexpected features entering the model. Choosing remainder behavior deliberately makes it easier to inspect outputs, understand which variables affect predictions, and explain the preprocessing process clearly. Python code remainder handling. This section shows how the ColumnTransformer handles columns that are not explicitly transformed. It compares the choice to drop those remaining columns with the choice to pass them through unchanged. It also emphasizes checking the resulting feature names so you can clearly understand which columns appear in the final transform data. We import pandas for working with tabular data and Scikit-Learn for machine learning preprocessing. Key tools include the ColumnTransformer for applying different steps to different columns, the one-hot encoder for converting categorical data, and the standard scaler for standardizing numerical features. Together, these imports prepare the data for effective transformation and scaling. We create a small pandas data frame to represent a customer table with 4 records. It includes numerical and categorical fields such as age, income, region, loyalty score, and notes. This mixed data setup provides a simple foundation for demonstrating data transformation techniques. We first define the expected customer data columns, such as age, income, region, loyalty score, and notes. Then we compare the data frame's columns against that expected set. If they do not match, an error is raised to flag unexpected columns, helping confirm the data structure before any transformations begin. A ColumnTransformer lets us apply different preprocessing steps to different data frame columns. In this setup, the age and income columns are standardized, so they have a mean of 0 and a standard deviation of 1, while the region column is one-hot encoded for use in machine learning. The output is made dense, any unused columns are dropped, and feature names are simplified for easier interpretation. A ColumnTransformer is used to apply different preprocessing steps to different columns. Numerical columns such as age and income are standardized with a standard scaler, while the region column is converted to numeric form with one-hot encoding. Any columns not selected for these transformations are passed through unchanged, and simplified feature names are used in the output. We compare 2 transformers on the same customer data. Both scale age and income and encode region, but one drops all other columns, while the other keeps the remaining columns unchanged. This shows the difference between removing non-transformed data and passing it through. To review feature names after transformation, convert each transformer's output into a list. With the drop remainder setting, the list shows only transformed features that were kept. With the pass remainder setting, it also includes columns passed through unchanged. Comparing the 2 lists shows how the remainder setting affects the final feature names. This section checks the Scikit-Learn version and reviews the original customer data columns before comparing two transformation settings. When the remainder is set to drop, only the selected columns are transformed, and all other columns are removed, so the output feature names and shape reflect just those transformed features. When the remainder is set to pass through, the selected columns are transformed, while the remaining columns are kept, producing a larger output. Comparing the feature names and shapes shows how the remainder setting changes which columns appear in the final transform data. This script shows how Scikit-Learn's ColumnTransformer handles columns that are not explicitly transformed. It scales numeric features and one-hot encodes a categorical feature in a small mixed-type customer dataset. When the remainder is set to drop, only the transformed features remain. When it is set to pass through, the untouched original columns are kept. The printed feature names and dataset shapes show how these choices change the number of output features. Composite details, sparse output thresholds. When combining feature transformations, the sparse output threshold controls whether the final result stays sparse or becomes dense. This matters because different steps can produce different formats, such as dense numeric features or sparse one-hot encoded features. Keeping sparse data can save memory when many values are zero, but the final choice also affects speed and compatibility with later estimators. Use the threshold as a guide for deciding whether to keep data in a sparse format. When a feature matrix is mostly zeros, sparsity can save memory, especially when mixing dense features with sparse ones. But if many values are non-zero, the storage overhead of a sparse format may outweigh its benefits, making a dense format faster and more efficient for modeling. When building nested composite estimators, you need to watch how sparse and dense outputs are combined. Different feature branches, such as numeric, categorical, and text processing, can produce different output types, and their combination determines the final data structure. Transformations like polynomial features or high cardinality encoders can change the overall density. Monitoring sparse thresholds helps control memory use, maintain estimator compatibility, and keep feature engineering practical. Python code, sparse output thresholds. This example shows how sparse output thresholds affect the final matrix format. When different feature blocks are combined, the result may switch between sparse and dense formats, and the printed densities help explain that decision. We import key tools for data preprocessing, NumPy and pandas for numerical data and data frames, a ColumnTransformer to apply different preprocessing steps to different columns, a one-hot encoder to prepare categorical variables for machine learning, and a standard scaler to put numerical features on a comparable scale. We create a small pandas data table with age, spending amount, and city information. It combines numeric values with categorical city labels, providing a simple dataset for showing how different data types are handled during transformations. The code verifies that the data table has 6 rows and 3 columns before continuing. If the dimensions are different, it raises an error to signal that the data is not in the expected format. This helps protect the example from running with incorrect assumptions about the data structure. We define pre-processing steps for different types of data. Numeric columns, such as age and spend, are scaled with a standard scaler, so their values have a mean of 0 and a standard deviation of 1. The city column is encoded with a one-hot encoder, which represents categories efficiently using sparse output. A ColumnTransformer applies the right preprocessing to each type of feature. Numeric features such as age and spend are standardized, while the city feature is one-hot encoded for categorical handling. Setting the sparse threshold to 0 forces the combined transformed output to be stored as a dense matrix. The dense preprocessor transforms the data by scaling numeric features and one-hot encoding the categorical feature. Because the sparse threshold is set to 0, the transformed output should be dense. The code then checks whether the result has a two-array method, which would suggest a sparse format, but this is not expected with the current setting. A column transformer is used to apply different transformations to different data types. By setting the sparse threshold to 1.0, its output stays sparse when the data is mostly zeros. This helps large, sparse datasets use less memory and process more efficiently. The sparse preprocessor transforms the data by combining numeric and categorical features into one matrix, which may remain sparse. The code then checks whether the transformed result has a method for converting it to a dense array, which indicates it is sparse. This confirms whether the preprocessing kept the data sparse under the chosen threshold settings. To find a sparse matrix's density, count its non-zero entries using the non-zero count attribute. Then compare that count with the total number of cells found from the rows times the columns. The result is the fraction of the matrix that contains non-zero values, showing how sparse or dense it is. The code gets the transformed feature names from the sparse preprocessor, then selects the first 5 for a quick preview. This helps inspect the output features without showing the full list. This demonstration shows how Scikit-Learn's composite sparse threshold affects transformed output. It reports the transformed data shape, measures overall density to show how many values are non-zero, and compares whether the result is sparse when the threshold is set to 0 versus 1. It also displays a few transformed feature names to preview how the output features are represented. This script shows how the sparse output threshold in a Scikit-Learn ColumnTransformer changes the format of transformed data. It standardizes numeric features and one-hot encodes categorical features, then compares thresholds of 0 and 1. A 0 threshold produces dense output, while a threshold of 1 produces a sparse matrix, which is useful when most values are 0. The script reports the output shape, density, whether the result is sparse, and a few transformed feature names. Feature name inspection. Feature name inspection connects transformed model inputs back to the original data and pre-processing steps that created them. This is especially important in complex pipelines with scaled numeric values, one-hot encoded categories, or text-derived features, where columns can otherwise become hard to interpret. By inspecting feature names, you can understand which meaningful inputs, such as regions, scaled age, or message terms, are driving model behavior and make debugging easier. In Composite Estimators, feature names help track how each pre-processing branch changes the data. Numeric, categorical, and text transformations may keep, expand, or create features in different ways. So merged outputs need names that show both the source data and the transformation applied. This makes it easier to verify that pre-processing matches the model design and to trace features back to their origins, such as admission type encodings or clinical note text features in healthcare. Inspecting feature names helps evaluate and maintain models responsibly. When a model behaves unexpectedly, feature names can show whether the problem comes from the data, pre-processing, or the estimator. They also help explain which inputs, such as business, location, or renovation features, are driving predictions. In complex pipelines, feature names connect transformed inputs back to the original data, making interpretation and collaboration easier. Python code, feature name inspection. Inspecting feature names in a composite feature space helps show where each transformed feature came from. A column transformer labels its output features, and printing those names makes the feature origins clear. We import pandas for working with tabular data, and Scikit-Learn tools for building a pre-processing pipeline. The setup includes tools to apply different transformations to different columns, fill missing values, chain pre-processing steps, encode categorical features, and standardize numerical features. Together, these imports prepare us to process both numerical and categorical data efficiently before machine learning. A small pandas data frame is created to represent a mixed-type customer dataset. It includes numeric information such as age, with one missing value, and monthly spending, along with categorical details such as region and subscription plan. This simple dataset is used as a starting point for demonstrating feature transformation techniques. The data is prepared using separate pipelines for numeric and categorical features. Numeric values are filled in when missing, and then scaled so the features are comparable. Categorical values are converted with one-hot encoding into a dense format that machine learning models can use. Together, these steps create a consistent dataset ready for analysis or modeling. A column transformer lets us apply different pre-processing steps to different parts of a dataset. In this setup, numeric columns such as age and monthly spend are imputed and scaled, while categorical columns such as region and plan are one-hot encoded. Enabling verbose feature names adds branch prefixes to the output features, making it easier to see where each transformed feature came from. The preprocessor is fit and applied to the customer data, carrying out the defined steps such as filling missing values, scaling numeric features, and encoding categorical features. This produces a transformed matrix where each row is a customer and each column is a processed feature. The feature names are then retrieved from the preprocessor to show what each transformed column represents. The code verifies that the transformed data has the same number of columns as the available feature names. If they do not match, it raises an error to signal a problem in the transformation. This check keeps the data aligned with its labels, which is essential for interpreting results correctly. This section checks the Scikit-Learn version for reproducibility, then reviews the customer data before and after preprocessing. It compares the original columns with the transformed data shape and feature names to show how preprocessing changed the dataset. The transformed feature names also reveal where each feature came from and which preprocessing branch created it, making the transformation steps easier to trace. This script shows how to view the feature names created by a Scikit-Learn ColumnTransformer. It uses a small dataset with numeric and categorical columns, applies imputation and scaling to the numeric data, and one-hot encoding to the categorical data. After transforming the data, it prints key information such as the Scikit-Learn version, original columns, transform shape, and sample feature names. The result helps show how transformed features are labeled by their processing branch and original source, making the final feature space easier to understand. Nested Composite Estimators. Nested Composite Estimators let you organize machine learning workflows by placing reusable preprocessing and modeling components inside one another. This is useful when different feature types, such as numeric, categorical, text, or date data, need different preparation before being combined for a final model. Nesting keeps the full workflow structured, reproducible, and easier to manage than separate manual preprocessing steps. Nested composite estimators make complex workflows easier to manage by giving each processing step a clear name, role, and place in the structure. This lets teams adjust or replace parts, such as scaling, encoding, or feature handling, without rebuilding the whole pipeline. The result is a modular workflow that makes it easier to understand how raw data is transformed into model-ready features. Nested composite estimators combine preprocessing and modeling into one training workflow, which helps prevent data leakage from steps like imputation or category encoding. Because the full workflow is treated as a single estimator, cross-validation and hyperparameter tuning can evaluate both the model and its pre-processing choices together. This makes complex pipelines more consistent, easier to debug, and more transparent, especially when tracing feature contributions for responsible deployment. Python code, nested composite estimators. Build a nested workflow that combines pre-processing and modeling, then inspect its key parts. Focus on feature names, sparsity, weights, and nested steps to understand how raw columns are transformed into model-ready features. These imports set up a machine learning workflow for processing data and building a classifier. NumPy and Pandas handle numerical data and data frames, while Scikit-Learn provides tools for pre-processing and modeling. The workflow includes transforming different column types, converting text and categorical data into numerical features, filling missing values, scaling features, and training a logistic regression model through a pipeline. We create a small Pandas dataset to represent customer information with mixed data types. It includes numerical age and income values, each with one missing entry, a categorical region field, and a text comment field for customer feedback. This simple dataset is useful for demonstrating basic preprocessing and modeling techniques. We create a small binary target array for the classification model. Each value, 0 or 1, represents the class label for a customer record. These labels will be used during training, so the model can learn how the input features relate to the two possible classes. Before training the model, the code verifies that the customer data has the same number of rows as the target labels. This confirms that every data point has a matching label, which is required for supervised learning. If they do not match, the code raises an error to protect data integrity and prevent training problems. For numeric data, we build a pre-processing pipeline with two key steps. First, missing values are filled using a simple imputer. Then, the numeric features are standardized so they have a mean of 0 and a standard deviation of 1, helping many machine learning models treat features more evenly. This pipeline prepares categorical data using Scikit-Learn's one-hot encoder. It converts categories into a machine learning-friendly format and is set to ignore unfamiliar categories during transformation, making the process more robust when new values appear. A ColumnTransformer is used to process different data types in one workflow: numeric data such as age and income, categorical data such as region, and text data from comments. Each group is transformed with an appropriate method, then weighted so numeric features count normally, categorical features count more, and text features count less. A sparse threshold of 30% helps store the transformed data efficiently when it is mostly sparse. We build a complete modeling pipeline by placing the ColumnTransformer inside it as the pre-processing step. This preprocessor handles numeric, categorical, and text features, then passes the processed data to a logistic regression classifier. Setting a random state makes the results reproducible, and the pipeline lets preprocessing and model fitting happen in one streamlined workflow. The model is trained by fitting the full pipeline to the customer data and target labels. Preprocessing first prepares the raw data by handling missing values, scaling numbers, encoding categories, and converting text into usable features. The logistic regression model then learns patterns between these features and the labels, adjusting its parameters to reduce prediction errors and prepare for new data. We retrieve the fitted preprocessing step from the model pipeline, then use it to get the names of the features it created. This helps show how the original customer data was converted into model-ready inputs. Finally, we apply the preprocessor to the customer data, producing a transformed dataset with the pipeline's cleaning, scaling, encoding, and vectorizing steps applied. This section checks key details of a Scikit-Learn pre-processing pipeline to confirm it is working as expected. It reports the library version, the numeric transformation steps, transformer weights, and the sparse output threshold. It also inspects the transform data shape, checks whether the result is sparse, and previews the first few generated feature names to show how raw columns become model-ready features. This script shows how to build a nested Scikit-Learn pipeline for a dataset with numerical, categorical, and text features. A ColumnTransformer applies the right preprocessing to each type, including imputation and scaling, one-hot encoding, and text vectorization, before fitting a logistic regression model. It also reports key pipeline details, such as transformer settings, feature space shape, sparsity, and feature names, to show how raw data becomes model-ready input. In this lecture, you learned to combine parallel transformations with FeatureUnion and MakeUnion, process heterogeneous columns using ColumnTransformer and column selectors, and inspect feature names, sparse thresholds, weights, and nested composite estimators. In the next module, Module 7, we will go over feature extraction.
Thank you for your attention. See you all in the next lecture.